Hello, 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 hello. So, hi everyone. I'm Devansh, and today we are going to discuss uh, the problems of today's contest, today's Leetcode Contest 488 weekly contest. And today we are going to discuss all four problems. So, yeah, let's dive in. So, for each problem, first we are going to understand the problem statement and what the problem says. Then we are going to jump in into the intuitions and observations we can make out of those problems, of those observations that we made at the problem statement. And then finally, we are going to jump at the solutions. So, yeah, let's start one by one. So, let's start with count dominant indices. So, you are given an integer array nums of length n. An element at index I is called dominant if nums I is greater than average of nums I plus 1, nums I plus 2, dot dot dot, nums n minus 1. Okay. So what this says, let's go here. If you guys have any problem, if you think you couldn't understand anything, if you want to share anything, you can ping it in the comments itself. So yeah, first question, what we got from the problems till yet. So first we are given an array nums of length n. So this is our array nums, and the length of the array is n. Okay, got it. And then an element at index I is called dominant, right? We are given definition of dominant. It's dominant if the element at index I, nums I, is greater than average of all the elements which are greater than it or which appear on the right side of it. So what's the condition for dominant? If this element is greater, strictly greater than average of all elements on right side of it. I plus 1 to dot 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 till the last element, n minus 1. Great, great. Okay, okay. Now what's the third point? Your task is to count the number of indices I that are dominant. Okay. The average, here's the definition of average, of the set of numbers is the value obtained by adding all the numbers together and dividing it by the sum of total number of numbers. Okay, great. The rightmost element of array is non-dominant. Okay, got it. So what else we got from the problem? We have to count such dominant indices. Count indices. Great. What indices which are dominant? Great. And what we have, there's also one more observation that the rightmost element is non-dominant. Okay, got it. So n minus 1 is non-dominant. Okay, non-dominant. Also, let's check the comment section. So, hey, hi, bro. Hi, hi, hi. Great to see you in today. Hi, thanks. How many problems you solved in the today's contest? I solved all four. So today we are going to basically discuss all the four problems. Uh, you solved two problems, I think, and someone solved one. It's fine. Like if you solve two or one problems, we are going to discuss all the four problems. And second one was little tricky too. So yeah, I stuck that two but solved one, three, and four. That's yeah. Second problem was little bit tricky compared to all three and four. Three and four, I think, was standard problems. And wasn't this more tougher than previous ones? Maybe some like depends on person to person. I use prefix sum for first. Okay, let's actually understand it. Okay, so this is the problem, right? We have four things. We have given an integer array, nums of length n, and we have to tell the number of dominant indices, right? This is our question. And what are dominant indices? Dominant indices are indices where the element value is greater than average of all the elements which are on the right side of it, or whose indexes are greater than it, right? So, and we have also given one more thing, that the last index is non-dominant. Okay, great, great. So these are the four statements that we have provided, and we have to find the number of indices which are dominant. Okay, let's observe some example, and as well as the constraint. The constraints of problem is pretty low. You can observe that the the length of the array is 100, like maximum 100, and also the maximum value of each element is at most 100, right? So this n is less than equal to 100 and greater than equal to 1 for obvious reasons, right? Let's take some example. This 543. Okay, let's actually understand the problem. 543, right? Now, how many indices we have? Like, how, what's the maximum number of indices that could be dominant? It could be this one and this one, right? Because this index can never be dominant, right? It's mentioned in the problem statement itself. So let's check for this index, right? So here, what we have to check, if 5 is greater than average of 4 and 3. 4 comma 3. How is average calculated? Average is calculated as sum of all elements divided by number of elements, right? This is the short notation for number. Yeah, this is the formula for average, right? So let's understand. The sum of all elements here is 4 plus 3. What is 4 plus 3? It's 7, right? And the total number of elements here are 2. So 7 divided by 2 is 3.5, right? So is 5 greater than 3.5? Yes, it is. Okay, great. So here we got our first indice, right? This indice is a dominant indice. Now let's check for this indice. So here on the left side we have 4, and we have to check if the average of 3 is strictly less than 4 or not, right? Yeah, let's check it. Like, it's pretty obvious, right? The average, if we have only one element, then the average would be 3 divided by 1. Sum of elements would be this element itself, and number of elements we have is 1, so this would be 3. So 4 is greater than 3. So yeah, this also satisfy our dominant indices definition, right? So now how many indices we have which are dominant? These are 2, right? So the answer here would be 2. Let's check. Okay, yeah, 2. There's also explanation here, right? So it's pretty straightforward question, right? We have to basically brute force check each indices, right? Let's say we are iterating from the start. For each indice, we got the left part, right? This is the element itself. And for the right part, we have to calculate the Hey everyone, hope I'm back. Hello, 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 hello. Okay, thanks, Anish. Yeah, yeah, sorry for issues. Let's actually get back. Let me just read the problems in the comment section until then. So, yeah, I use prefix number first. There are 3 and 4 standard. Yeah, 3 and 4 are standards. Yeah, 3 and 4 were actually standard problems. I solved 4 by 4 in the first 20. I solved 1 to 4 in 20 minutes and spent 20 more minutes just to solve number 3. Yeah, third one was actually also like little bit tricky. Apart from it, my rating will become 2102. Very great to. Okay, okay. So yeah, so let's actually begin again. So yeah, coming on to the topic, like, did you got the like the major intuition here was the same, right? What we are going to do, we are going to basically we have, let's say, three numbers, 5, 4 and 3, and what we are going to do for each index, we are going to find out if it's greater than the average that exists on right side of it, right? This is the logic. So how are we going to implement it? We have two ways. Either we could like iterate from here and check for each like index. uh, for each index we could calculate this sum, right? And we are basically, to find the average, we are going to divide it by the number of elements that are on the right side, right? Let this be m, the number of elements which are on the right side, and check for each index, right? So it's like pretty straightforward. Let's actually also see my solution for it. If you guys like feel any part that needs more clarification, just ping me out in comments. I'm actively seeing the comments. Yeah, it will be recorded too. This is like a YouTube live stream. It would be surely be recorded. So don't worry about it. So yeah, what I did was, either we could iterate from here, either we could iterate from here. What I planned was, let's iterate from last to first. So we'll start iterating from this index, right? And we'll keep a sum variable. Initially sum would exist this element 3. Why? Because this element 3 could never be a dominant index, right? So we'll start iterating from here. We'll keep this sum variable, and we'll check if for the sum variable we have divided by number of elements on right, which would be I minus n minus 1 minus I, right? And minus 1 is the last index minus the current index we are, tells us how many elements are on the right, and we check if the current element is greater than it or not, right? It is here clearly shown by my code. So just as I said, here we have variable n, which tells us number of elements in the nums array, and then we have this sum variable, which is basically updating itself after each iteration by the current element, and it checks also. Like, this is basically a better way to do it. Instead of dividing it here, we could just multiply it here, right? It's what we need to do. We need current elements. We need to check if sum divided by number of elements on right, right? Instead of checking this, we could also multiply it here, right? This same thing I have done here. I have multiplied this element itself by number of elements on right, and check if that is greater than sum or not. If this value is greater than sum, we are basically incrementing the answer, and then we are returning the answer. Clean sweep, guys, right? Now let's move to the second question. I hope this was clear. This was like pretty, it was an easy problem, right? Doubt I doubt anyone would require no clarification, but if you need, you can just ping it out on the comments. I'm actively checking out comments. Now let's move towards the second question. This was actually a very good question, by the way. Yeah. You are given an integer array nums. Okay. You must repeatedly apply the following merge operation until no more changes can be made. Okay. 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 So this is question number 2. Great. 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 Okay. So we are given an integer array nums. Okay. And we have to basically apply some operations. Let's understand what operation it is. If any two adjacent elements are equal, choose the leftmost adjacent pair in the current array and replace them with a single element equal to this sum. Okay, great. Okay, so basically we have this nums array, right? And then was the second observation here? We can perform some operations. Perform operations, right? And for each operation, what we have to find is basically we have to check if two adjacent elements are equal. That means, let's say our array looks like this. We have to check if any two elements are equal, and if they are equal, right, we have to choose the leftmost pair. Leftmost pair is this, right? We have to choose the leftmost pair. First we have to check if it's equal, then we have to check the leftmost pair, and then we have to merge it. What does merge mean? We have to add it. We have to, instead of this, after one operation it would become a to b, this value c c d. We basically merge this value b plus b, right? This is b plus b. We delete both elements, and instead of it, we basically put the sum of both values in this place. Got it? This is operation. Okay, let's move further. Hi Adarsh. uh, After each merge operation, the array size decreases by 1. Okay, repeat the process on updated array until no more changes can be made. Return the final array after all possible merge operations. Okay, got it. So we have, okay, we have told that we have this array and we have to perform these operation until, what is the third point? Until we can't anymore. Got it? Got it. Is there any problem with the question? So basically what we have told is we are given one nums array and we have to perform this operation. What is the operation? We have to find adjacent equal elements, and for the leftmost pair of adjacent equal elements, we have to remove it, and instead of it we have to replace it by its sum. We have to merge it, right? What's the question? Merge adjacent equal elements, right? It speaks for itself. So this is what we have to perform, and how are we going to perform it, right? So now let's actually see some observations. Let's actually understand the question more by some example. Let's take this 3112. 3112. So what would be the operation here? Again, only pair we have is this one. These two are equal, as it's the only pair which has adjacent, where adjacent elements are equal. We are going to, instead of this, we are going to replace it by its sum. So the array would become 3 2 2, and we have to return this array. Right, we have to return this array. One more example. Let's actually make this example by ourselves. We cannot find this example. Is also a very beautiful example. 2 2 4, right? So in the first operation, the only pair we see which are equal is this one. So instead of this, we are going to place it by its sum. So what would be its sum? 2 plus 2 is 4. Someone in the comments said we can use stack. Yeah, surely we can use stack. So yeah, this becomes 4 comma 4 after an operation. Again, this again becomes equal, right? So we again can use it. So instead of this, we are going to use its sum. It could be 8 here.
So this is the final element, right? So again, these two examples we tried, and we what are the observations here, right? Can we brute force it? Let's actually also check the constraints. The constraints are the length of the array is 10 raised to power 5. Okay. And for each element, the value of each element would be less than equal to 10 raised to power 5. Okay, great. So basically, can we brute force? Let's actually start with brute force. Brute force. Can we brute force? Can we brute force? Let's think. If we have to brute force, let's say we brute forced here. So we had to iterate entire array for first index where we find out that the both elements, adjacent elements are equal. We have to stop, and then we have to create a new array, right? We have to create a new array. We have to copy all elements on the right. We have to copy all elements on the left. And instead of this element, we could just add its sum to the new array, right? What would be the time complexity for each operation? The time complexity for each operation here would be O of n, right? Because we need to copy entire array. And how many max operations can we have? Let's say we have an array. Let's say we have an array. 2, 2, 4, 8, 16. So here 2 plus 2 would be 4. And then again we have to perform the operation. 4 plus 4 could be 8. Then again we could have to perform the operation. It could be 16. Right here, let's say it's 2, 2, 4. Again we have to make sure these operations are also satisfied, right? So in this way, like, but we cannot perform this operation yet, right? This would be again 2, 2, 4, and then 8, 8, 16, then again 2, 2, 4, right? You're getting the point, right? If this is, let's say it's length is n, right? The total number of operations could be as large as n. Can I say that? Can I say that? Let's take one more example. Let's say the entire array consists of 2, 2, 2, 2, 2, 2, 2, 2, and 2. And we have 10 raised to power 5. We have n elements, let's say. Right? For first operation, you are going to perform the operation on this. And then for second operation, you are going to perform operation on this. The total number of operations would be n by 2, right? And each operation takes n time complexity, and we are going to perform it by n by 2, so it's going to take n square by 2, like in this case, right? But can we perform n square, can we perform this question in n square time complexity? No, we cannot. Why? Because we have tight constraints. We have the length of the array can be less than equal to 10 raised to power 5, right? We have tight constraints. So this was the brute force solution, right? Every time I iterate the array, find that index, copy the entire array to a new array, and then apply operation on that array, right? Now let's optimize this. Let's optimize this. How can we optimize? How can we optimize it? How can we optimize it? So to optimize it, what we could do is basically let's start iterating the array. Let's say we have this array 2, 4, 4, and then we again have 2 and 3. Let's say, right? For each operation, let's say we are at here, we are till here, right? If let's say for each element, what we are going to do, we are going to take a stack here, right? And in this stack, what we are going to check if the last element is equal to this one or not, and we are going to iterate from the starting. So what how is this going to help? So basically, if let's say the stack, currently the stack would be empty, right? This 2, is it equal to the last element of the stack? As currently stack is empty, it's not. So we are going to push it. So here the 2 would be, and then we move forward. We check for 4. Is this equal to the last element on the stack, which is 2? No, it's not, right? So again we are going to push it, and then for 4 we can check, oh yeah, this is equal to 4. So we are going to basically pop this out, and instead of this we are going to put in 8, right? We are going to check for 8, and this way we could move forward, right? How did we optimize it? Like, still it's like little unclear. One thing that you have to, let's go for this test case: 8 4 4 2. Something interesting about this test case is after operation 1, what you did was you took 4 4 and placed 8 here, right? Now if let's say we are iterating from here and we are going to perform operation each time we found two duplicate elements. So we are iterating from 8 and then we reach 4 comma 4 and then we perform operation here. Now we turn this to 8. Great, we turned it to 8. Now we, if we move forward, we forget that the previous element 8 was, now these two elements are equal, right? And there could be this element 16 here, right? After performing even on this 8 8, it's 16. Now we have to we have to also see that the element which is again the previous element, is it equal to or not, right? This is the first observation, right? This is the first observation. The first observation is that we cannot like move forward and keep going forward. We have to also check for the previous elements if the current after making operation, if the current element is equal to the last element or not, right? So this is our first observation. Our second, like this is the only like operation that we require, that if we are iterating from the leftmost element to the rightmost element, we are, every time we reach out to a point where we see two equal elements, we can perform this operation. And instead of counting them separately, we can make them, merge them to a single element 8. Now our concern is we have to also make sure, instead of moving forward, we are also checking if the previous element, right, this 4 4 made 8, we are also checking if the previous element, which is in this case 8, is equal to it or not. If it's not equal, then we can move forward, right? How we can deal with it? Yeah, let's actually talk about it, right? So this is the entire observation that we need to solve the problem. The first observation is, let's say we are going to iterate from left to right, because we have to make the leftmost operation first, right? And then we have to also check the previous elements. These are actually the two observations that is sufficient to solve the problem. And how are we going to basically perform the problem? Let's again go. 16 8 4 4 2. Here there's one more observation. We only require the previous element, right? We don't require 16 now. We only need the previous element. We need the last element that we iterated, right? What does it sounds like? What does it sounds like? We need the last element. Anish said like, how can we deal with it? Anish, how are we going to, how are we going to make sure that we have some data structure, or we are storing it in a way that we only have the last element, we only require the last element, right? So we could use a stack here, right? For this, for checking out the previous elements, we could use stack, right? Because the stack would tell us the last element we had, and this stack would be used to check the current element we are having after operation, right? Stack, right? So what's the observation here? Observation is we are going to keep a stack, and we are going to keep an iterator. We are basically going to iterate from first to the last element, and for the first element we are going to check if the last element on the stack, is it equal to this or not. It's not equal, okay, we are going to put it. Then we go to this, is it equal to 16 or the last element? No, it's not. We are going to put it. Now we reach here, is it equal to 8? No, it's not equal to 8. Okay, great. uh, is it equal to the last element? Oh yeah, this is equal to last element, right? 4 and 4. So what we are going to do is we are going to pop this out, and instead of this we are going to update it we are going to add it plus 4, and this would be 8 here. And now again, instead of moving forward, we are going to check for this index itself. Is this element equal to the last element we have? Now 4 is being popped out. We have 8. Is it equal? Yeah, they both are again equal. So again, we are going to pop it out 8. We are going to add this by 8. We are going to update it by 8, or we are going to merge it. And then we have 60. For now, 16. Is it equal to the last element? Yeah, again it's equal to the last element. Again, we are going to pop it out. Again, we are going to add it. We are going to update the current element, and then it would be 32. Now, again, we are going to check. Now the stack is empty, right? This is the updated stack. Now the stack is empty, right? So yeah, we don't have any elements, so we are going to place it here. Now we move forward to the next element, 2. Is 2 equal to 32? No, it's not equal to 32. We are going to push it in the stack. And then we are going to basically pop the stack out by any means, and then we are going to print this array, or we are going to return this array, right? So this was the entire solution for it, right? Let me actually also explain it through my solution or my code here. Got it. So what we are doing here, okay, got it. Yeah, let's say, let me check the comment section. So I solved all for grade, dude. Great, good for you. You can still watch the stream. You can see if you're like, if I come up with something new, or if you think you came up with something new and something easier, you can ping it out in the comments. We have to put while condition to check all previous elements also. Yeah, exactly. So what how I did here was, first I take two vectors, answer and a vector v. Instead of stack, I'm using vector here. You know that, like, we can use vector as stack, right? Like, if you're not aware, we could use answer dot back is same as checking the last element of the stack, and dot pop back is same as like popping out from the stack, right? So basically I'm using here vector answer. The vector answer is our stack, right? It's the same thing, right? It's the same thing. Now this is our where our main magic happens. So long a tells us the first element. I'm just the nums array, we are not, I'm just like, what I'm doing is placing all elements of nums array into a vector v. Why? Just because like I like it, right? I don't want to use nums again and again. And also there's one more logical reason which I will tell in the end. So what we are going to do is, basically we are going to check if answer dot size is greater than 0. That means that we are checking the size of the stack if that's greater than 0. If the stack is empty, what we do, we are going to pop it. We are going to push the current vector, current element in the stack, right? If the stack is empty, or if it's not equal to the last element, we are going to push it in the stack, right? But what if the last element is equal? Right, if the last element is equal, we are going to pop the last element. We are going to update the current element. And let's someone mentioned in the comments we can use while loop. Instead, what I'm doing is I'm basically reducing the current iterator by 1. So when the loop reaches to the its end, it will basically increment my iterator, and we will be at the same place. Got it? So this is the entire solution for it. You can use stack, it's the same thing. Like, if you could, we can use vector as stack, or you can use the literal stack itself, right? So this was the entire solution. And yeah, one more reason why I used long, why we are actually transferring the all elements of nums to vector, this vector v, is basically, in this vector the type of each integer is long, right? You have to make sure that here you are updating your current element. As you're updating your current element and it starts from 10 raised to power 5, there might be a case that the value of this would increase the integer limits, right? That's why I'm actually pushing it to a vector, and then I'm using this. So each value, instead of integer, I want the value to be to of each element to be long, so it is capable of handling all the merges. That's all. That's all. Like no other thing. I don't think even that would cause problem. But yeah, when you are in the contest, the only thing that matters is that you are able to solve the problem like fast as you can. Later you can optimize, you can learn from your mistakes, right? It helps in the long game. So this is just an good observation like you can make every time when you are updating. Make sure like if the vector we are using it, right, and that comes from the params, if that might explode, we could actually just copy it somewhere, right? So yeah, let's move to the third question now. Hope this question was clear. If you have any doubts, you can ping it out in the comments. I'm actively checking out comments. Yeah, let's move to the third question. This was actually good question. Like these two questions were pretty standard, what I thought. But this one was actually like, yeah, you have to think some, you have to like take some time to think, and it was like pretty good question. Now let's move to this question. It was like pretty small question by the way. So yeah, third question. You are given an integer array nums, an integer k. Okay. For any subarray, define its cost as cost equal to max of nums l r. This is basically tells us the subarray. Subarray which starts from index l and ends the index r. Right. This is the notation for it. So basically, the cost is the maximum of nums array. Okay, the maximum element in the array starting from index l to r. Okay, maximum element of the subarray. Great. Minus minimum of nums l r. This again, this is the subarray. So minimum element of the subarray into r minus l plus 1, which is the size of the subarray. Got it. So the cost is maximum element of the subarray minus minimum element of the subarray into cost of the subarray. Right? For any subarray, this is the notation for it. We define this cost as this. This is the cost. Okay, great. We got about the cost. Return an integer denoting this number of subarrays of the nums whose cost is less than equal to k. Okay, got it. Again, we have this nums array. This is the third time we are having it. Yeah. And and what we have to find out, the cost of the array, cost of any sub array is maximum minus maximum element, right? Maximum element in the sub array minus minimum element, and this entirely into size. This is cost of sub array, right? It's written here in the mathematical form. It's written here in mathematical form, right? So we are just simplifying it, right? To make it simple. And what we have told is we have to find number of subarrays whose value is less than equal to k. Less than equal to k. Okay, great. So this is our third question. We are giving a nums array, and we are given that cost of any subarray is the maximum element in subarray minus minimum element in subarray into size. And then we have to find the number of subarrays whose cost is less than k. Cost, right? Number of subarrays whose cost is less than k. This we have to find out. And this is given. Right. Let's move to the problem. Let's actually take some example. 1, 2, 1, 3, 2, and k equal to 4. Okay. So k is here equal to 4. and the array we have is 1, 3, 2. Right? Let's check for each subarray. Right? Let's check for all subarrays that end with 1. Just for example, let's say. So the number of subarrays that end with 1 are 1. Right? The cost of it would be the maximum element that it has, which is 1, minus the minimum element it has, minus 1, into the length of the subarray, which is 1, which is equal to 0. Right? Is 0 less than 4? Less than k? Yeah, it is less than k, right? So we got our 1. So this is our first subarray that satisfies the problem. Now, let's take uh, are there any more subarrays which end with this element? No, they are not. Let's move to the second element. This is 3. So here we have two subarrays, right? This subarray 3 also ends with this element, and this we have 1 comma 3 2. Why are we checking like number of subarrays that end with this? We can also check like the number of subarrays which start with this, right? It doesn't make a problem. It's the same thing. We just do this, that so we make sure that we cover each subarray, because each subarray would have some ending, right? It would have its ending might be this element itself, its ending might be this element, its ending might be this element, right? So in that way, if we keep on tracking from the first element itself the number of subarrays from that end with this, then this, we make sure that we cover all the subarrays, right? For this, what would be its cost? Its cost again would be 3 minus 3, because when there are one element, the maximum minimum element is the same, so the difference would be 0 into 1. So again this is 0, which is also less than k, which is equal to 4. Right? What's the cost of this? Here things becomes pretty good. Here things becomes interesting, right? Because the max element is 3, the minimum element is 1, and what's the size of it? It's 2. So now the cost is 3 minus 1 is 2. This is equal to 2, right? 2 into 2, it's equal to 4. Is 4 less than equal to k, which is also equal to 4? Yeah, right. K is equal to 4. Great. That means that this also satisfies the equation. Now we move to the all elements which end at 2. Right? So these are 2, the element itself. That now we have 3 comma 2, and we have 1 comma 2. 1 comma 2 comma 3, sorry. Right? What would be its cost? The cost would be again 0, as we calculated above. What would be its cost? It would be the maximum element minus minimum element into the size, which is this is 1. 1 into 2 is 2. 2 into 2 is 4. Is 4 less than equal to 4? Or k? Both are same, right? K is 4, 4 is k for this given problem. So yeah, this is also great. So this is also satisfied, this also satisfied. Now let's check for this equation, right? Now here maximum is 3. Minimum is 132, right? Again, yeah. The maximum is 3. Minimum is 1. Into total number of elements are 3. 3 minus 1 is 2. 2 into 3 is 6. Right? 2 into 3 is 6. Is 6 less than equal to k, which is equal to 4? No. No, right? Clearly not. No. So what's the answer for it? 1, 2, 3, 4, 5. So the answer for it would be 5. Let's actually check it here too. Yeah, the answer is 5. In the same way, they also concluded for each subarray what would be its cost, and then they check if its value is less than equal to 4. Right? Hope you got the question here now. So basically, what this is the question, right? So what we could do here? How could we solve it brute force? Whenever any problems Whenever you solve any problem, let's check, always check how could we solve it brute force. Sometimes the constraints are so low that we could basically solve it brute force, and we are just thinking and just tirelessly how are we going to solve it in less constraint, but we don't even require it. Okay, so let's actually see the constraint. The constraint is the length of the array is less than equal to 10 raised to power 5, and for the value of each element is less than equal to 10 raised to power 9, and the value of k is less than equal to 10 raised to power 15. These are the constraints, right? They are pretty high constraints. So how are we going to, the n is less than equal to 10 raised to power 5, and k is less than equal to 10 raised to power 15, right? So how are we, n is the length of nums, by the way. Nums length, right? How are we going to solve this brute force? Right, it's pretty obvious. Like, we can make all the subarrays that ends at 1, then 3, then 2, right? And then for each of them we could calculate the cost. We would calculate the maximum element in it, we would calculate the minimum element in it, and then we are going to check if it's less than equal to k or not, right? Right. So what we could do is calculate all subarrays, calculate all subarrays, right? Basically get all subarrays. Calculate would be get, right? Basically calculate for all subarrays, or first get all subarrays and then calculate it. What would be time complexity to get all subarray? Let's say we have 1 3 2, right? The number of elements which end from here would be, let's say, 1. The number of elements which end from here would be 2. Let's say we have more elements, right? We have till n elements. So the number of elements that end at this here would be 3 dot 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 dot, and the number of elements which end with this is n. Right. What are total number of subarrays? The total number of subarrays would be the sum of it. Right. The sum of it would be 1 plus 2 plus 3 dot 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 plus n. Right. And what's this is like the famous sequence, right? The famous computer programming sequence. If you're not aware of it, whenever you see this sequence 1 plus 2 plus 3 plus 4 dot 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 n, like all the elements till starting from 1 to n, we are basically summing it up. The We have a formula to calculate this. So the formula for calculating this is n into n plus 1 by 2. Got it? So this is a famous formula that we can use. I am assuming most of you are already aware of it. If you are not, that's not a problem, right? So again, can we find these many subarrays, right? We cannot, right? This is n square, right? The value of n is 10 raised to power 5. We cannot go n square, right? Yeah, we cannot. We can basically calculate all the subarrays and then check the maximum and the minimum element in it. It's pretty easy, but we cannot perform it due to our current constraints, right? So we don't have enough time, right? The compiler in 1 second, the thing with it is it can solve at most 10 is to power 7 operations. Around that it could perform, right? But this 10 is to power 5 into 5 would go 10 is to power 10, right? We cannot perform it, right? So how are we going to solve it, right? How are we going to solve it? We have to make few observations first. What observation do we have to make? What else we could do? So let's first actually check this subarray. Did you notice something? Did you notice something? If, let's say, this all the elements starting from 2, if it's superset, this array includes this one, right? This array includes this one, right? So if it's subset, or if it includes this one, if this is true, this would be always true. Can I say this? Can I say this? Can I say this? Let's say we have this subarray 1 3 2. The cost of it would be, the cost of it would be the maximum element, right, minus the minimum element, which is 1. And let's say we multiply it by the length of the array, which is 3. So this would be 2 into 3. So this would be equal to 6. Let's say for this array, this is this array, and k equal to 6. Can I say that, let's say we did it for this, where we are ending at this, right? If for this largest subarray for 132, it satisfies, then for any subarray ending with 2, right, which has less elements than this array, or any suffix of this array, right, it would always be true. Can I say this? Right. For each suffix, this is going to be true. Right. The k for here is 6. For each suffix, it's going to be true. Let's also check it. The suffix are 3, 2, and 2. These two subarrays. For this subarray, the value would be 3 minus 2 into 2, which is equal to 2. And for this, the value would be 2 minus 2 into 1, which is equal to 0. Could you please repeat the suffix bar? Yeah, sure, sure, sure. So basically, what I'm calculating, yes, is basically, let's say we took this subarray, right? We with the problem. What's the problem here? Let's actually understand this. The problem is we cannot check for all the subarrays, right? When we were checking it, well, let's say our ending point is this. We check for all subarrays which end with 1, and then we check for all subarrays which ends with 3, right? But doing this would take us n square time complexity, right? So I'm figuring out, so we have to figure out, how can we optimize this, right? Let's say we ended this. Can I tell somewhere like this, or this element, after this element we cannot take it, right? I was thinking in these terms, like I was thinking in these terms, how can we optimize it? How can we optimize the number of subarrays, right? One dry run. Yeah, yeah, sure, sure, sure. Sure, sure, sure. Let's actually explain, understand this part more deeply. Let's say, let's say we had this array 1, 3, 2, right? And we started from here. We started calculating from all the subarrays which ends from 2, right? For this array 1, 3, 2, the cost would be the maximum element 3 minus minimum element into the size of the element, number of total number of elements or size of the subarray, which is 6, and this is less than equal to 6. Right, case this is our new test case, let's say, right? For any suffix of it, this suffix is all elements starting from 2 which has less elements, which is, this was our entire array. I'm talking about this and this subarray, right? So this is 3, 2, and 2. What would be the value for each? It would be 2 and it would be 0, right? For any suffix of it, the value, the cost we get would be always less. Can I say this? Can I say this or not? Right. How did I came to it? Let's actually, this is our first observation. If you can't understand, let me actually give you a very good case here. What I'm saying is, let's say we have this two elements, right? Two elements and k equal to, let's say, 8, right? What is the cost of these two elements? Cost would be equal to 3 minus 1 into 2, right? So this would be 2 into 2, this would be equal to 4. Yeah, great, great. But let's say I added one more element here, right? Let's say I did 4 here, and now we have to calculate for 1, 3, and 4, right? Tell me something. After adding one more element, would the cost would increase or decrease? Right? Yeah, yeah. Someone said, I see all subarrays ending with 2 will have cost less than equal to k, right? Yeah, yeah, yeah. Right, right, right. But let's actually see this. This is a second observation, which is actually these two observations are the major observations. We can, after analyzing this second observation, we'll move to the first observation again, and I'll make sure that both observation are demonstrated completely, and you get it completely. Okay, so what I'm saying is, when we add new element, what happens to the cost? Does it increase or decrease? Does it increase or does it decrease? What happens? Right, the cost is equal to maximum element minus minimum element into size. Right, when we add any element, right, the here observation is, when we add element to our subarray. Yeah, someone said it increase. Okay, let's actually assume it. What happened when we add element to a subarray? Let's say we had 1 3, and we added 4, right? Or we added any element instead of 4. What will happen? What's the formula here? The formula is cost of maximum into minimum into size, right? We can see that this would increase, right? Because size increases, we added one more element, right? Would this increase or decrease? the, if we add any element, right, we could either increase the maximum, we could either decrease the minimum. Both ways it increases. Either that element would be between the maximum and the minimum, and that would not make any difference, right? So here, either there would be no difference, no effect, or this would increase, right? So this is a observation. When we are adding for any subarray, when we are adding any element, this would this is surely going to increase the cost. Why? Because we are going to multiply it by size, right? This would surely increase the cost, or it could be equal to it. When would be this equal to it? This is this edge case here. The edge case here is, let's say we have one element 3, and we added 3 here, right? Still the maximum is 3, the minimum is 3, and the size is equal to 2. We increase the size, but the cost is 0. The cost of 3 was 0, and this is also 0, right? That means that the cost will either increase, but either it will remain same, either it would increase, right? So this is our first observation. This would either increase or remain same, right? Right. This would either increase. This is C here, right? Don't mind. Okay, so when we add any element, this would either increase or the cost would remain same. Got it? So using this observation here, we can also say, when we are checking for the last element, if again the vice versa is also true. What happened when we remove any element? We are going to decrease it, or either it would remain same, right? Right. This vice versa would also be true. When we remove any element, we are going to either decrease it, or either it will be same. So what, using this observation here, we could say that for entire array, if this is equal to true, then all its suffix it would be true, because we are basically reducing one element, right? For each suffix it would be true, right? So this is another observation we make, right? This is a first observation that after adding any element, we are going to increase its cost. After removing any element, we are going to decrease its cost. And here we made the observation that using this observation, we made that for each suffix. Let's say we are calculating for all the subarrays which end with 2. For if it agrees for this, it's gonna agree for all the elements less than it, right? So these are two are major observations, right? Right. So what are the observation? First, if we add or on adding or removing element, what's going to happen? It would either on adding element it's going to increase, on removing element it's going to decrease. Got it. For any subarray, for any subarray, if it's true for this subarray, right? If it's true for this subarray, if the cost of this subarray is less than equal to k, then for any subarray inside it, subarray inside inside it, the cost would be less than equal to k. Can I say that? Right? These two observation are major observation. Now how this these two observation can solve it, right? So now let's say we have any elements, any number of elements. Let's say we have this pattern what we calculated here, 132, right? What we are going to do is for each index, let's say we start from 1, 3 and 2. Let's actually do it here. 1, 3 and 2. For any subarray, I'm going to calculate, like for any index, I'm going to calculate the minimum index, right? Till where the subarray, the cost of subarray is less than equal to k, right? So I'm basically finding out the largest subarray or the largest subarray which ends with this, whose cost is less than equal to k. And what this would give, this would basically help me if that subarray is that subarray is true, that subarray, the cost of subarray is less than equal to k, then any part of it would be also less than equal to k, right? If any part of it is less than equal to k, then any suffix I take would be also less than equal to k, right? Let's say for if k is equal to 6 here, for this subarray, what is the value of the cost is 3 minus 1 into 3, right? The cost is equal to 6. If for this subarray, it's let's say we are checking for all subarrays that ends with 2, right? Then I could say that the minimum index that we could go is here, right? And then if this entire subarray, the cost of subarray is less than equal to 6, then for any suffix, either 2, either 3 comma 2, either 1 comma 3 comma 2, it all would be true, all of their respective costs would be less than equal to k, right? Right. So basically I'm just, again we are going to iterate from first to last. Let's say we have this array 5, 1, 3, 2. For any index, I check what could the minimum index I could take such that this subarray is true. If this subarray is true, I'm going to basically in the answer variable we have, I'm going to mark all the subarrays whose suffix, all the suffix of this subarray is true, because we are basically checking for all subarrays that end with 2, right? So we are going to check for all, we are going to check for each indice, right? So this will include all the subarrays and this would tell us the answer. But how are we going to find it? The one thing that that will come to your mind is, we for each index will keep on adding this index and we will keep on recalculating the cost, right? but this would take a lot of time, right? For each index we have to go backwards, right? This would be n square solution. So instead of this there are two approaches that we could follow. Right, there is this approach we could follow, which is also the major hint for it. We could use two pointer. How are we going to solve it by two pointer? How are we going to solve it by two pointer? Let's actually check. Let's say again 5 1 3 2. We are going to keep both pointers on the left, and we are going to check if this subarray is, if this subarray is valid or not. If this is valid, we are going to increment the r. We are going to place the r here, and we are going to check if this subarray is valid or not. And if this subarray is valid, all the suffix of this subarrays are also valid, right? So again we are going to check for each r, right? If the starting if from the L to R, if this subarray is valid or not, right? And the point there is, if let's say this subarray is not valid, if we are going to add one more element, it would never be valid, right? If for the next element we are going to check for ending 3, right? For ending 3 it would also be not valid. Why? Because if this is not valid, we are adding one more element here, which would make the cost, the cost would be same, either it would increase, right? So this is the major observation here, right? This is the major observation here, right? We are going to keep two variables, L and R. We are going to check for L and R, right? If cost is for cost, if the cost is less than equal to K, answer plus equal to all suffixes, right? Because if this subarray is true, all the suffixes would be true. Otherwise, if the cost is greater than K, we are going to increment the we are going to increment the Lth index, right? And remove one element. Basically, remove. In this way, using this algorithm, we are going to find out all the subarrays whose cost is less than equal to K. Right, right. Let me also show you using the one solution that we already ran through. Okay. So yeah, this. But how do I get to solving problem in contest where I can solve till the second only? Okay. So here this was observation here. Here you're going like for this problem, you would have to go step by step, right? How did we solve the problem, right? How did we solve the problem? First we understood the problem, then we took a case and we understood the case. Okay. Then we thought like how could we solve it using brute force, and then we optimized it. How did we optimize it? We made this observation that when we are going to add any element or when we are going to remove any element, what's going to happen. Using this observation, we also made this observation that the suffix of any subarray would also be true, right? As we are going to calculate for all the subarrays which ends with 3, right? Like we calculated it here, right? To get all the subarrays, right? Using the same logic, we combined both logic and we got this. For any subarray, if the cost is less than equal to K, for any subarray inside it or for any suffix inside it, right, its cost would also be less than equal to K. Using these two observations, we came to the fact that we could basically use two pointers and solve this problem, right? So again here too, what let's actually dry run this algorithm, and then we'll move to the next question. 3 1 2. Let's say L is here, right? L is here, L is equal to 0. We are using zero based indexing. R is equal to 0. The subarray is 3. The cost of 3 is 0, right, which is less than equal to, let's say k here is equal to 4. Less than equal to 4, right? So what we incremented in the array, we incremented the suffix, which is it has only suffix, only one suffix, so we incremented by 1, right? Now we incremented the right pointer, so this would be L equal to 0, R equal to 1. So the subarray we had was 3 comma 1. I'm actually to calculate the maximum and the minimum element, right? The length would can easily, we can easily calculate the length, right? This would be R minus L plus 1. So to basically, what I'm doing is using a map, a frequency array, a frequency map or dictionary in Python, and there I'm storing it, the frequencies of each element, right? So when we are basically deleting it, I would delete it from the frequency array. In this way, I would, as map sorts all the element on basis of keys automatically, I can easily find the first and the last element, which would be the minimum and the maximum. So again here, this would be 3 minus 1, and the size of array would be R minus L plus 1, which would be equal to 2. So here it's 4, which is again less than equal to 4. If this is also, if the cost of this subarray is also less than equal to 4, then we are going to add plus 2, because it has two suffixes, right? It has this suffix and it has this suffix. How are we going to calculate the number of suffix? It would be actually equal to the length, right? Number of suffix is equal to length of the array, right? Similarly, again, as it's true, we are going to increment it. L is again equal to 0. And now we have 3 comma 1 comma 2. Now things are interesting. Why? Because the cost here is 3 minus 1, which is equal to 2, into 3, which is equal to 6, which is greater than 4. As it's greater than 4, that means that we need to reduce its size. So we are going to increment this. So here this would be L equal to 1, R equal to again 2. So this is 1 comma 2, right? Now the cost of this would be, it would be obviously it would be less, right? We removed the one element. So this would be 2 minus 1 into 2. This would be equal to 4, which is less than equal to 4. Now we can use this subarray, right? We can use all the suffixes of this subarray. The suffixes would be the length of the array, right? Length of the subarray, right? And then we are, which here is 2. So we added 2 here, we added 2 here, we added 1 here. The total answer would be 5. So we got our answer, right? Let's actually also see the code for it. Yeah, so this is basically, I'm just pointing out the size of the subarray. This map is basically, I'm storing all the elements, right? Because this map is going to sort all the elements by the key. So we can find the maximum element and the minimum element in logarithmic time complexity, or we can find it quickly, right? So here, first what we did, we made two pointers LNR, and we made our answer equal to 0. Then what we did, we basically, here map, we put the last element, the rth element in R map, and we check the value for it. The value for a value or this is our cost, right? For the cost would be the largest element. This is how we check the largest element in the map, or the largest key. This is how we check the smallest key, into the maximum minus minimum into the size, right? We check it, and then if this cost is less than equal to k, we add all suffixes. We add all, and if it's not, right, we go here. What we go here, we are basically incrementing the lth pointer. The L pointer we are going to increment, and then we are going to increment it till when? Till the cost is less than k, right? Until the cost is greater than k, we are basically going to erase the leftmost element, right? Here we erase the leftmost element, and then we again recalculated the cost. and until the cost is uh, less than equal to k, we are going to remove the leftmost element again and again. So what we did here, remove the leftmost element. Right, right. So, and then at last we returned the answer. After each iteration, we updated the rth index and then we updated the answer. Right. So this was very beautiful problem. Right. Both the second and third problem was very beautiful. The fourth problem was not that, like, it was pretty cliche or like standard problem. Let's actually also study this. Right. Let's move to the fourth problem. Let me just check out the comment section first. If you guys have any doubt, you can ping it out in the comments. Oh, I see you are solving the problem. I can solve till second only. Yeah, great. Let's move to the fourth problem. Okay, let's go. So you're given two integer arrays, okay, nums1, nums2. Again, the nums. So yeah, I have the length n and m respectively and an integer k. Great. You must choose exactly k pairs of indices. Great. Such that each pair of each indices that we choose is for this is less than equal to n, this is less than equal to m, and for each chosen pair I comma j you gain a score of nums1 into nums2 j. Okay, the total score is sum of products of all selected pairs. Return an integer representing the maximum achievable total score. Okay, okay, great. So let's actually extract from the problem. Right, so we are given two integer arrays. First is nums1 and another is nums2. Right, and then what we have given is we have to take k pairs, right, exactly k pairs, right, such that k pairs of, let's say we have I1 comma j1 and then ik comma jk, and these k pairs, what does each pair tells? This, using these pair we are going to calculate the score. And what's the score? The score is basically nums1 in I1, right, into nums2 j1 plus nums1 I2, right, into nums2 j2, and similarly for all k pairs. This is the sum. Got it. Got it. So we, what we have and what we have to find out, right? We have to find out maximum sum. So this is the question, right? First, let's understand the question. So we have two arrays and we have to take k pairs. Each pair is like this. Each pairs are basically indices, right? Like these, and then we are able to calculate the score. The score is nums1 into the first indice that we chose in this pair of the nums1, and then second indice we chose of the first indice we chose of nums2, right? So this can easily be translated as k pair of elements from both. Got it. Got it. Got it. Got it. Got it. Right. Let's actually take one example. We have 1, 3, 2, 4, 5, 1, and k equal to 2. 1, 3, 2, 4, 5, 1. Right. What we have to choose is what does this tell? This tells us that we have to choose k elements from here, and we have to choose k elements from here, and we have to basically the elements we choose. Let's say we have to multiply those k elements by these k elements in the same order. Got it? Got it. So one time I use segment 3 in third problem in Maxon when in particular subarea. Yeah, segment 3 is like fine, like I think it's an overkill for the simple problem. During contest, we don't think a lot about optimization. We only care about solving the problem. But yeah, this can also be solved by using normally dictionary or map or set even, right? But yeah, set we would not be able to calculate the frequency. So yeah, map would be I think the perfect. Yeah. But if you guys did something better, or if you guys use some alternate approach, you can always ping it out in the comments. So yeah, back to the problem. So we are going to choose k elements from here. We are going to choose k elements from here, and then we are going to multiply those corresponding elements. Let's say we took this and this element from here, with this and this. We are going to multiply it corresponding to the order of the elements we have chosen, and then we are going to add it. The sum of them would give us the answer, and we have to get the maximum answer we could get. Right. For this question, let's say we took this and this. What would be the pair? We took 1 comma 5 in one pair, and then 3 comma 1 in one pair. We have to choose indices as pair, right? So indices would be this is 0th if we are taking zero based indexing, and this is 1, and then this 3 is 1, and this is 2. This is the indices we choose, but we can always deduct to this problem, right? That we have to take k elements from here, then k elements from here, and then we have to basically multiply it corresponding to their order of the elements we have chosen in each array, and then after multiplying them, the cumulative sum of each pair would be the answer, right? Here what would be the sum? What would the score? The score would be 1 into 5 plus 3 into 1. This would be 5 plus 8. 5 plus 3, which would be 8. Right? Can we do something else? Right? Can we do something else? Yeah, we can. We can you choose these two elements, right? What if we choose these two elements? Then this would be 3 into, and we choose these two elements here. Right? So this, the pairs would be, it would make 3 comma 4 as pair. And the second pair would be 2 comma 5. So 4 into 3 is 12, right? And 5 into 2 is 10. Adding both, it would be 22. Is 22 greater than this set? Yeah, this is greater than it, right? So this would be our answer. Most probably, like we can check for all different occurrences for all them, and then we have to find the answer. Let's check the answer. Is it 22? Yeah. Yeah, it could be, it couldn't be. Like we have to check for all possible cases. Yeah. Also, let's check the constraints of the problem. The length of n is would be less than equal to 100. The length of m would also be less than equal to 100, and for each value we are given that the value would be minus 10 raised to power 6 to the 10 raised to power 6 positive, right? Make sure that the elements could be negative 2, right? The elements could be negative 2. Okay, great. So how are we going to solve the problem, right? This is the problem, this is the test case, and now let's actually also write the constraint, right? And k is also less than equal to 100. K is actually less than equal to minimum of n comma n. Yeah, it's mentioned here. Okay, so these are all things we are given, right? I'm not like preparing something, these are already here. These are already here. These are already here. Okay, great, 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 great. So how are we going to solve the problem? Can we like any problem that occurs to us, we can solve it either by DD, either by using some recursion, or like we what's the procedure? First, we find the brute force, right? How are we going to find it? How are we going to solve it brute force? Right? What's the brute force for it? Right? What's the brute force? Check for all pairs. Check for all. Right? The brute force is check for all. We basically, for all k indices in the nums 1 and all k indices in nums 2, we basically check for all possible cases, right? How could we check this? Like how are we going to check this, right? The number of elements here are m, the numbers of elements here are n, right? How are we going to check this? Like, the one idea is we could use recursion. But why recursion? Like, check for all, yeah, it's yeah, we are using brute force here. One thought that might occur to many of you is, why are we not using greedy? We could use the maximum elements here and the maximum elements here, k maximum elements here, k maximum elements here, and the answer would be our answer. Right, right. It might occur to some of you, but that's not the case here. Right. Greedy would fail actually. Our first observation would be, let's take maximum k elements from here, maximum k elements from here, and then find out. Right. This would actually not work. Right. Let's actually also find out if there is some test case for us. Okay. Yeah. Because we never know what k elements to take. Right. We never know what k elements to take. Okay. Let's actually first understand the recursion, then we'll get back to this point. Okay. Again, the brute force check for all. Right. How are we going? We could use recursion. Right. How are we going to use the recursion? We could basically check for all indices. Let's say current, we have two arrays, right? Nums 1 and nums 2. Right. For each indice, what I could do is basically make a recursion function here, and for each function I would have this I, which will tell us the current element we are pointing to. Right. This J will tell us the current element we are pointing to in our second array. Right. This is the ith element, this is the jth element, and k number of pairs that are left. Right. Number of pairs that are left. Pairs left. left, right? Right. And then we could, using these three variables, we could calculate, we could whenever we find some match, whenever we are pairing it, like this is, let's say, this is our pseudocode, this is our recursion function, right? And if, like, let's say we are pairing it, we are going to multiply it, nums I into nums j, 2 here, this would be 1, and then we are going to basically add it, I plus 1, j plus 1, and k minus 1, because we already made one pair. Right. Using such kind of recursion, we could actually find all the elements, right? We can find all the pairs. Right. But is it the best way to do it? This is the brute force way, right? This would surely work. Right. This would surely work. But this is not actually the most optimal solution. Right. We find out that we could actually check for all different pairs, right? And for checking for all different pairs, we come to the conclusion like we could use either greedy. right? When we came to the conclusion that we are going to use greedy, we are going to use recursion, we came up with such a formula that we would have this ij which would tell us the current element we are pointing to, and we'll start from 0 comma 0, and then we will check we are if we want to make the pair, either this we are going to make the pair, either not, we would basically just we would increment the ith pointer, right? So basically we would do I plus 1, we will keep the j as it is, and we'll keep the k is the number of pairs left, right? So we haven't chosen any pair yet, so this would be same. Either we could also increment the jth pointer, so here i's remain same, j and k, right? And we'll basically calculate it, right? But this is nowhere near efficient, right? Because we have this, the value of this would be around 100, this would be around 100, this would be around 100, right? So what can we do? There would be like many overlapping cases here, many overlapping cases here. So whenever you find out this situation, you find out like using recursion or using something you did that, now we need to optimize it, right? What we could do is we could use dp here, right? What is dp? One like this thing really helped me was dp is just optimize recursion. Recursion, this problem is a pretty standard problem. Like if you are able to solve second problem, if you are able, like if you know about dp, you could easily solve it, right? So but what I like, how did I thought like let's actually move to brute force, and brute force we could use recursion, but this would take a lot of time. So how are we going to like optimize it? So then I came up with the dp, like using whenever you are stuck somewhere where you can find all the possible cases you can recursion, there might be some chance that you could use dynamic programming to basically optimize it. Why dp here? Why dp here? What we could- why are we using dp here? You know that for any recursion that we are having, right, the state of recursion can easily be calculated by these three variables. Yeah, right. The states can easily be calculated by these three variables. That means that what are the total number of states? Total number of states would be the number of like the number of I we could have, the number of j we could have, and number of k we could have, right? The maximum value would I would be 100, and for j would be also 100, for k would be also 100, right? The maximum value for these three. Cumulative, what's this value? 10 is to power 6. Can we perform 10 raised to power 6 operation in 1 second, or whatever constraint we are given? Probably it would be 1 second. Yeah, it's around that. Yeah, sure. It's acceptable. This is acceptable. This is acceptable. Great. If this is acceptable, that means that using this recursion, we just have to use dynamic programming and store all the states so it doesn't overlap. Right? It doesn't overlap using this 3D vector, because we have three indices, right? We have three states, three things to maintain, right? These three decides the states, right? Using this and storing these values, we could basically uh, get ourselves rid of the overlapping parts of the problem, and then we could optimize it to this time complexity, right? For like whenever you need to think in terms of db, calculate the states. What are the possible states that could occur, right? The possible states that would occur is this: 100 into 100 into 100. There could be 100 different types of I, 100 different types of j, 100 different types of k, right? And using that, we calculated that there are total 10 is to power 6 different states. And then using this can easily be calculated in our given time complexity, right? Right. So we are just going to memorize it. How are we going to memorize it? For any answer, what I'm going to use, I'm take a 3D vector, and for any answer that we have, we are going to store it. For every state we are going to store it. Our answer would be some of these, right? Some of these. So our answer would be some. And when we enter an array, when we enter this recursion, we are going to see if this dpi j k is available or not. We have already calculated this subtree or not, or we have already calculated this state or not. If we have already calculated this state, I'm going to return this. I hope this is clear and like completely. So how did we approach the problem? We first understood the problem and we deducted it. The problem is basically we take k elements from the first array, k elements from the second array, and then we are going to multiply it in the order of the elements we have chosen, right? So we took, like, can we apply greedy? There are few test cases we'll discuss that will fail on greedy. So then we think, okay, what's the first procedure to solve any problem? We check what's the brute force of it. We check the brute force. The brute force comes out to be recursion, that we recursively find out all the pairs that could happen. And when while we are recursively finding it out, we can actually store it. We came to the conclusion that this recursion is not that feasible. We have to optimize it. To optimize it, we came to the conclusion we could use dynamic programming. What is dynamic programming? Is basically storing the states, right? So basically, we are just storing the states here. And then after, when we enter any recursion, we check if it's already been calculated, this state. If it's already been calculated, we return it. If it's not been calculated, we calculate it. And then we are going to store it in our, then in our 3D vector. Hope this is also clear. If you have any doubt, you can ping it out in comments. I'm actively checking it. Let me meanwhile explain my code. So this is our entire recursion I have called. So first I calculated the recursion. Let this for your reference. Let rename this variable recursion. Right. We have three states I, j, k. This is a vector nums1 and nums2, and this is our dp 3D dp vector. First, we check if we have already reached this to the endpoint or not. If we have already at the endpoint, if k is equal 0, that means all pairs are used. If all pairs are used, we return 0. Otherwise, if all pairs are not used, that means we are not going to use this. We return min. Min is actually a least possible number that we could have. Right? Why? Because we are not going to use this branch anymore. Right? We are not going to use this branch anymore at any case. Then we again move forward. We check if k is again equal to 0. K is equal to 0. That means all pairs are used. If all pairs are used, we return 0. Otherwise, if this state is already been calculated, if state is already calculated, if state is already calculated, that means that we don't need to calculate it anymore and we return this as it is. Otherwise, we are going to basically calculate it. I took three different portions. This portion, we are going to actually multiply both values, and this is the same, right, as we discussed. Right, in this we are just increasing the iterator for the first array. This is, we are going to increase the iterator for second array. Here we are going to increase the iterator for both arrays because we choose the current iterators as the pair. Right, as we are choosing this as the pair, we also reduce the k by 1. And then we are storing it, storing the maximum value that we could got from all three states, all three possible choices, into this dp. And then so other, like, again, if the state occurs, it's going to detect if the value of the state is already stored or not. If it's already stored, it's going to return it from here. What is this extreme? This is the value when this is a default value. This is not going to ever occur due to any state, right? Because, like, ideally, what Standardly we put up -1, but we could here get the value of as -1, right? For some, let's say for some pair, right? That's why instead of -1, I'm putting it extreme. Extreme means that this value is never occurred. That means we haven't calculated it yet. We haven't calculated using this state yet, right? And we are going to return it. And here we return it. If you guys have any problem, like if you guys have anything you want to discuss, if you think you have better solutions, you can actually ping it out in the comments. You can actually tell me all, like in the comments itself, right? It's super cool, right? Let's actually end the stream here, right? So these were the four problems here that we discussed here. Like my favorite one was the second problem, actually, not the fourth or third one. Second problem was pretty good, I think. Pretty good observation you had to make here. And yeah, like all problems were beautiful, yeah. So thanks for Leetcode for such beautiful problems. I think now I'm going to end the stream. If you guys have any doubt or something, you can actually put it down in the comments. I will be watching comments after the stream too. So it doesn't matter. I'll be active in the comments. Yeah. Hope you love the problems. See ya.